Welcome back to section 4 of chapter 8. This is the last section in the chapter, so it's a pretty short chapter. And this one is on improper integrals. Improper integrals take there's a couple things that fall into this category, but for the most part, it's an integral where you have infinity as a bound. So it's kind of weird because we're finding like the area under the curve as it's going off to infinity. Um, As you can possibly imagine, based on what we've just been doing, this is going to involve limits. So our learning targets for today, we're going to evaluate improper integrals. We're going to determine whether integrals converge or diverge using the comparison test, use integrals to find perimeter area or volume, and then which we've done now, it just might go off to infinity, so it's the same thing, and answer conceptual questions proving or proof statements involving improper integrals. So, improper integrals, as I mentioned, it's just an integral where we have infinity as a bound. What do we do with this? Well, we're not going to take it as it goes to infinity, but what we can do is we can plug in a number, let's say b, of e to the negative x over 2 dx, and then we're going to take the limit as b goes to infinity. So we're not going to deal with infinity and the integral in the same step. We'll find the integral, and then we'll deal with infinity. So we'll have the limit as b goes to infinity of e to the negative x over 2. The antiderivative of e to the something is going to be e to the something. So we still have e to the negative x over 2 divided by the derivative of the exponent. The derivative of that is going to be negative 1/2. When we divide by negative 1/2, that's the same thing as multiplying by negative 2. And we're still going from 0 to b. So we'll take the limit as b goes to infinity. We're going to plug in b. So we have negative 2 e to the negative b over 2 minus plug in 0. When we plug in 0, e to the 0 is 1, so we have negative 2, so that'll just be plus 2. And now we will take the limit as b goes to infinity. So I'm going to rewrite this, that e to the negative. Let's rewrite that really quick. We're going to go b goes to infinity. E to the negative means we'll have negative 2 over e to the b over 2 plus 2. Now we plug in infinity. We're going to have negative 2 over e to the infinity. That's 0 plus 2, which is 2. So the area there is 2, which is kind of strange because when you think of it, the area, it goes on infinitely far, so it's always adding stuff. But it's adding stuff that's getting smaller and smaller and smaller, and so it's not changing that total area much once it hits that a certain point. And so the area under this is 2. In general, our improper integrals, which have infinite integration limits, if it's continuous, and that is important, it has to be continuous here. We will deal with something where it's not continuous in a minute. If we're going from a to infinity, then we go from a to b, take the limit as b goes to infinity. If we're going from negative infinity to b, then we'll go from a to b, and we'll take the limit as a goes to negative infinity. If we have both, then we're just going to split it up somewhere in the middle. We'll go from negative infinity to the number, and then from the number to infinity, and we will add those two things together. A good place to split it up is a lot of times 0, sometimes 1, something that's going to be a decent thing to plug into the equation. So let's take a look at one of those. We'll go from negative infinity to infinity of e to the x dx. So we're going to split that up. We'll split it up at 0. So we're going to have negative infinity to 0 of e to the x dx plus 0 to infinity of e to the x dx. Then for this, we'll have to take the limit on both sides. So we'll have the limit as a is going to negative infinity from a to 0, e to the x dx, plus the limit as b is going to positive infinity, 0 to b, e to the x dx. The antiderivative of e to the x is just e to the x. So we'll have limit as a goes to negative infinity of e to the x from a to 0 plus the limit as b goes to infinity of e to the x from 0 to b. We can plug in the zeros and a's. So we'll have limit as a is going to negative infinity from, so we plug in 0, we get 1, e to the 0 is 1, minus plug in a, we have e to the a, plus the limit as b is going to infinity of plug in b, we have e to the b, minus plug in 0, e to the 0 is 1. Take the limit as e goes to negative infinity, that minus e to the a, well, let's see, we have 1 minus e to the negative infinity, that's going to be 1 over e to the infinity, which is 0, plus, plug in infinity, we have infinity minus 1, which is infinity, so we have a whole bunch of stuff here, but we're adding infinity, so there's no limit. It's infinite, it's improper, it diverges. That's a vocab word. It diverges if it comes out to be infinity, like when we're adding them together. For this case, if either of them came out to be infinity, it diverges. It converges if we get a number. Like that first one we did, it converged to 2. So one of the things we'll be doing is checking to see, is it diverging or converging? Like this one right here. So we're going from 1 to infinity of 1 over x dx. Does it converge or diverge? So we're going to have to find it. We'll have the limit as b goes to infinity, 1 to b, 1 over x dx. We're going to find the antiderivative of 1 over x dx, which is just natural log x of natural log x, 1 to b. Technically, it's an absolute value of x, but both of our bounds are positive, so that does not make a difference. It goes to infinity, we will plug in b, so we have natural log b minus natural log 1, and natural log of infinity minus natural log 1. The infinity is that's infinite, so this also diverges. It comes out to be infinite. That means it's going to diverge. So another one, we have 0 to infinity of 2 over x squared plus 4x plus 3 dx, or maybe it diverges. So how do we deal with this? This is one of those partial fraction deals. So we're going to have the limit as b goes to infinity of 0 to b, but we're going to have to figure out our partial fraction. So first step, we need to factor that denominator, x plus 3, x plus 1 dx, which means we can split it up. 0 to b, we'll have a over x plus 3 plus b over x plus 1 dx. And we know that when we multiply, a times x plus 1 plus b times x plus 3 has to equal 2. So we have ax plus bx, so a plus b times x plus a plus 3b has to equal 2. Well, we have 0 x's, which means that a has to equal negative b in order for that to be at 0. So negative b plus 3b equals 2. That's 2b equals 2, so b equals 1, which means a has to equal negative 1. So back to our partial fractions. We'll take it up here. Limit as b goes to infinity, 0 to b of a, which is negative 1 over x plus 3 plus 1 over x plus 1 dx. Antiderivative. We're going to have natural log of x plus 3 plus natural log, oh, that's a negative natural log of x plus 3 plus natural log of x plus 1. And we're going from 0 to b. So we can plug in b. We get natural log of b plus 3. I'm going to move that negative to be a negative 1. Plus natural log of b plus 1 minus plug in 0. We have negative natural log 3 plus natural log 1. So now when we take the limit, we're going to have infinity plus infinity. That's no good. So we're going to combine these first two with the b's. So when we combine these two, we get natural log. When we add, that means we multiply. So we have b plus 1 over b plus 3 because of that negative exponent. Then it's plus natural log 3, and then minus natural log of 1 is just 0, so we don't need to worry about that. So as b goes to infinity, this b plus 1 over b plus 3 goes to 1. Natural log of 1 is 0, so we end up with natural log of 3. So the indefinite integral in this case turns into natural log of 3. And this one required partial fraction decomposition. Are they all going to require partial fraction decomposition? No, but a couple of them might, which seems like a pretty good chance to practice our partial fraction decomposition, because it's been a little while and it's good to repeat some of that stuff. Same kind of idea here. This isn't partial fraction, but in this case, we're going to have to do some integration by parts. So our integral from 0 to infinity, we're going to have the limit as b goes to infinity of the integral from, oh, not 0, but 1 to b of x e to the negative x dx. So we can let u equal x and let dv equal e to the negative x, which means du equals dx, and v, the antiderivative of e to the negative x, is negative e to the negative x. So our integral, I'm going to ignore the limit part for a second. The integral from 1 to b of x e to the negative x dx will equal uv. So we have negative x e to the negative x, and we have to go from 1 to b, plus, well, minus the integral from 1 to b of v du, but that's a negative e to the negative x. That's plus e to the negative x dx. We know what the antiderivative of e to the negative x dx is. That's negative e to the negative x. It's going to go from 1 to b. Negative x e to the negative x goes from 1 to b. Just 1 to b. X e to the negative x dx. So we can plug in b. Plug in b here, we get negative b e to the negative b minus, plug in 1. So minus that negative is going to be plus 1 e to the negative 1 minus, plug in b, e to the negative b minus, so minus e to the negative 1. So that's going to be plus e to the negative 1, 1 to b, x e to the negative x dx. Now we can take the limit as b goes to infinity. And when we do this, we get negative infinity, but e to the, this is that over e to the negative infinity, or positive infinity, plus e to the negative 1 minus 1 over e to the infinity. I'm changing the exponents to be positive, plus e to the negative 1. So this one's 0, because we have 1 over infinity. This one's not quite. This one over here, we have infinity over infinity. So for that little piece, we're going to have to do something else. L'Hopital's rule. So we have negative b over e to the b as the limit as b goes to infinity. So b is the variable here. We can take the derivative, top and bottom. So that'll give us the limit as b goes to infinity of negative 1 over e to the b, which is negative 1 over e to the infinity, which is ends up equaling 0. So all we have left are these guys. We have 2e to the negative 1s, or 2 over e. So the area under the curve from 1 to infinity of x e to the negative x dx is 2 divided by e. So it's a little bit less than 1. That, again, we used integration by parts, so we could remember what integration by parts is. Also, L'Hopital's rule was thrown in there because we had an infinity over infinity for one little piece. We don't need to use it for the whole thing. We only used it for this piece right here. We were able to L'Hopital. The rest of it we didn't need to because it didn't fit what that was. So we have those. What if we have the whole thing? We're going from negative infinity to infinity. Well, we just have to split it up somewhere in the middle, probably 0. So we're going to take the limit as a goes to negative infinity of a to 0 dx over 1 plus x squared plus the limit as b goes to infinity of 0 to b of dx over 1 plus x squared. Now we can find the antiderivative of the 1 over 1 plus x squared. If you remember your antiderivatives, that is an inverse tangent. And it'll be the same over here. We have inverse tangent, 0 to b. Now we can start plugging stuff in. So we plug in 0. So we have inverse tangent of 0 minus inverse tangent of a. And this we have the limit as a goes to negative infinity, plus we'll have the limit as b goes to infinity, inverse tangent of b minus inverse tangent of 0. The inverse tangent of 0 is 0 because when it's 0, tangent 0, so that's 0. Minus inverse tangent of negative infinity, as it's getting closer and closer to negative infinity, we're getting closer and closer to negative pi over 2. Because remember, the inverse tangent has those horizontal asymptotes at negative pi over 2 and then positive pi over 2. So this one, as it goes to infinity, this is turning into pi over 2 minus 0. So here we have minus negative pi is plus, so we have pi over 2 plus pi over 2 gives us pi. So when we have negative infinity to infinity, we have to split it up somewhere in the middle. 0 worked really well here because it equals 0. It was a value that we know. We could have used something else. We could have used at 1. That could have worked. That would have been a pi over 4 for both of them. It would have canceled each other out. We would have had pi over 4 minus pi over 4. So it doesn't have to be 0, but 0 tends to be a good place. What about integrands with infinite discontinuities? Now, this doesn't mean we have an infinite number of discontinuities. This means that somewhere in here, it's going to go to infinity. For instance, this one, from 0 to 1, if we graphed this, it would graph something like this, where we've got that vertical asymptote there. So it's kind of like when we had the horizontal asymptote, but now we actually have 2 asymptotes. So what do? We do basically the same thing. We can't plug in 0 to this because 0 doesn't work, but we can take the limit as a is going to 0 from the positive side of the integral of a to 1. It's the same thing. We're just not going to infinity. So as we are doing this, we have to find our antiderivative here. A is going to 0 from the positive side. The antiderivative, this is x to the negative 1/2 dx. So we're going to add 1, so it'll be x to the 1/2. divide by the new exponent. So divide by 1/2, same as times 2. From a to 1, we're going to plug in 1 minus plug in a. So you have limit as a is going to 0 from the positive side. Plug in 1, we have 2 times 1 is 2, minus 2 times root a. A is 0 and it's positive, so we don't have to worry about the whole negative square root thing. But as it's getting closer to 0, that square root's getting closer to 0, so 2 times 0 is 0. So this just leaves us with 2. So that integral there, even though it has that vertical asymptote that we're counting, it still just comes out to be 2. We do it the same way we do it when we're going to infinity. We just take a limit as it's going to that point. In general, this is what it looks like. So this is another type of improper integral because it has something going to infinity. So again, it's continuous. We can split it up if it's both that we have to deal with, or if it's something in the middle. If it has so in this bottom one, it's continuous on AC and CB, but there's that point C in the middle that it's not. We just split it up at that discontinuity. We'll see a problem like that in just a minute. So here's the problem. Evaluate the integral from 0 to 3 of x minus 1 to 2/3. So here, this is going to have a vertical asymptote at x equals 1, because that's what makes the denominator 0. So we're going to have to go a limit from we need a variable here. We'll go a. A is going to 1 from the negative, and we'll go 0 to a of, I'm going to switch this to be x minus 1 to negative 2/3 dx plus the limit as a goes to 1 from the positive side, a to 3 of x minus 1 to negative 2/3 dx. So find the antiderivatives. We'll have limit as a goes to 1 from the negative side. We're going to add 1, which makes this x minus 1 to the 1/3. And then divide by the new exponent, which is 3. 0 to a plus limit is a is going to 1 from the positive side. It's going to be the same deal. We're going to have 3 times x minus 1 to the 1/3 from a to 3. So we're going to plug in our values. So we plug in a. So we're going to have 3 times a minus 1 to the 1/3 minus 3 times plug in 0, so that's 0, so negative 1 to the 1/3 plus the limit as a goes to 1 from the positive side, plug in 3. 3 times 3 minus 1 to the 1/3 minus plug in a. 3 times a minus 1 to the 1/3. And now we can take the limit. So let's plug in that value. So plug in 1. So we have 3 times, well, that's 0 to the 1/3 is 0. Minus, so we have 3 times negative 1 to the 1/3. So the cube root, it keeps the sign, so that's negative. So that'll be just a plus 3. Plus, we have 3 minus 1 is 2. To the 1/3 is the cube root of 2 times 3. So this is just 3 times 2 to the 1/3 minus, plug in 1. Well, 1 minus 1 is 0, so that's okay, and that's just 0. So we have 3 plus 3 times 2 to the 1/3, which is just what it is. 2 to the 1/3 could also be the cube root of 2. So 3 plus 3 times 2 to the 1/3, or 3 plus 3 times the cube root of 2, means the same thing. Notice these get big and ugly in the middle sometimes. That's okay. They're going to get big and ugly in the middle. You just have to keep organized. Handwriting is an important thing. If your handwriting is bad, all of a sudden stuff tends to change on you. So here we're going from 1 to 2 of 1 over x minus 2. So it's continuous up to 2, but not at 2. So this is the same idea, except it's just an endpoint again. So we're going to go limit as b goes to 2 from the negative side of 1 over b, 1 over x minus 2 dx. Antiderivative of 1 over something like that's going to be a natural log x minus 2 dx. The absolute values here are important. From the negative. One to b. So we can plug in b. Natural log of b minus 2. Oh, that didn't need a dx anymore. Minus, plug in 1. Natural log of 1 minus 2. So as we go to the 2 from the lower side, we subtract 2. We're going to get a negative, but it's going to be 0. So this can be natural log of 0 minus natural log of negative 1. Natural log of negative 1, or natural log of 1, because we have the absolute value, is 0. But the natural log of 0 is infinite. So this diverges, which means that it doesn't actually have a value. So evaluate, a lot of times the directions say evaluate if it converges or indicate that it diverges. So this one diverges. So the area under it is in fact infinite. Tests for convergence and divergence. The test is basically if you compare it. So it's a comparison test. You have these three things. If g of x is bigger than f of x, which is positive, if g of x converges, if the big one converges, then the small one converges. If the small one diverges, then the big one has to diverge. It does not say anything if the big one diverges or if the small one converges. But if the small one goes to infinity, then the big one goes to infinity. If the big one goes to a value, then the smaller one has to go to a value. So what could we use it? So does the antiderivative of 1 to infinity of e to the negative x squared dx converge or diverge? If it converges, estimate its value using a calculator. So the first thing is we can't actually find the antiderivative of this because e to the negative x squared is not something that we can readily do. We would have to use a calculator to do that anyway. And so we can't get an equation that we can find the limit of. So does it converge or does it diverge? Well, e to the something is always going to be positive. So we have that. And then we just need to find something that's similar to it that's always going to be bigger than it or smaller than it. What's similar to e to the negative x squared? E to the negative x. And we can do e to the negative x. In fact, we have done e to the negative x. E to the negative x does converge. If we graphed both of these, we'd have a graph that looks like this, where the red one is e to the negative x squared, the green one is e to the negative x. E to the negative x is bigger than e to the negative x squared from x equals 1 and on. So from that point on, it is bigger. Notice it does not have to be bigger all the time. It has to be bigger after a certain point. For x bigger than a, in this case a is 1, it's always bigger. And so if the area under the green one has an area, that means the area under the red one has an area. This spot here, well, that's a finite area, so that's not going to change the convergence or divergence part of this. And in this case, it actually just starts at 1 anyway, so it's always bigger for where we care. So it does converge. It converges because e to the negative x squared is always greater than 0, because that's important. It has to be greater than 0. And for x is greater than 1, e to the negative x squared is less than e to the negative x. And e to the negative x converges. We could test that if we needed to. That's going to be the limit as b goes to infinity of 1 to b, e to the negative x dx. The antiderivative of e to the negative x is going to be negative e to the negative x from 1 to b. Limit as b goes to infinity. Plug it in. We'd have limit as b goes to infinity of negative 1 over e to the b minus negative, so plus e to the negative 1. And then as it goes to infinity, this one goes to 0, so we're left with just 1 over e, which is a value, so that converges. So since that converges, e to the negative x squared is smaller, then e to the negative x squared has to converge. What does it equal? This does not tell us what it equals. To figure out what it equals, we would want to graph it and then just see where our asymptote is. It's going to get closer and closer and closer to something. So we just need to get bigger. So this is going to use a calculator or Desmos. We're going to graph it and using the numeric integral, and then just find bigger and bigger values. And so here when we graph it, it actually flatlines super fast. So it gets that asymptote very, very quickly. As we're looking, it's getting closer and closer to about point. Where's my value? It's getting closer and closer to about 0.3. No, 0.139 is what I have. I only get 3 decimals looking at where I'm at Desmos, but 0.1390. It's getting closer and closer and closer to that. And so the 1 to infinity of e to the negative x squared is going to be about 0.1394. Where'd my value go? Yes, 4. 0. Fun fact, if you actually do have the use of Desmos or you want to check your answer, you can actually type this into Desmos and it will calculate the value for you. So if you want to graph it, change the infinity in the upper bound to like a b, and it'll graph it for you. But if you plug it in as infinity, it will find the value. So with that, I will see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.